In this video, we are going to see how Ito formula can be used to prove that certain processes are martingales and then use them in various applications. So let's do a first example. So our first example is the process t goes to exponential of alpha times the Brownian minus alpha squared over 2 times t. And alpha is a parameter which can be any positive number. So we are about to show that this process, let's call it x, defines a martingale. So in order to do that, we consider a function of r plus cross r into r that sends t and x to exponential alpha x minus alpha squared over 2 times t, and our process xt is going to be f of t dt. So in order to show that xt defines a martingale, that's for every t in 0, 1, we need to do two things. So if we can show, one, that dt ftx is equal to minus 1/2 dx squared of ftx for all t in 0, 1 and for all x in r, and two, that the expectation of the integral from 0 to 1 of f of t bt squared dt is finite, then 1 plus 2 implies that xt is a martingale by Ito formula. All right, because Ito's formula would be telling us that xt is dx of that dxt is the integral from 0 to t of dx of ft bt dbt. So you would be a Ito integral of an H2 process. Property 2 guarantees that this is in H2, and property 1 guarantees this equality because the other terms in Ito formula cancel each other thanks to property 1. So we have to prove 1 and 2, and we could deduce from 1 and 2 that xt is a martingale with respect to the Brownian filtration. Okay, so these are two fairly concrete things to check. Let's check them. So proof of 1. Okay, well, we just need to compute the partial derivatives. What is dt of ftx? This is minus alpha squared over 2 times ftx, because ftx is defined as an exponential of alpha x minus alpha squared over 2 times t. So this is what happened when I differentiate with respect to t. What about dx? Well, if I differentiate with respect to x, then I just pick up an alpha. And if I differentiate twice with respect to x, then I pick up alpha 2 times, so I get alpha squared. Right, so we have all of that, all for every t in 0, 1, and for every x in r, just computing the partial derivative. So 1 holds, right, because dx squared of ftx is certainly equal to minus times minus 1/2 is certainly equal to dt. Okay, now what about 2? All right, so I have to compute the expectation of the integral from 0 to 1 of alpha squared times exponential 2 alpha bt minus alpha squared t dt. Okay, so let's compute that. Now we know that the Brownian increments are Gaussian variables, so this expectation is really the integral from 0 to 1 of 1 upon square root of 2 pi t times the integral from minus infinity to plus infinity of alpha squared exponential to alpha x minus alpha squared t times exponential minus x squared over 2t dx dt. Right, that's because bt is an n0t variable. Okay, so we need to compute that. And what can we say about that? We can write that as the, so all I need to show is to show that it is finite. So in order to do that, I'm just going to say that exponential minus alpha square t is so smaller than 1, alpha square and square root of 2 pi's. These are just numbers. And then I have the integral from 0 to 1, the integral from minus infinity to plus infinity of exponential 2 alpha x minus x squared over 2t dx dt. And in order to compute this integral, what am I going to do? So I could complete the square, or I could, I'm just going to complete the square. So I'm just going to say that this is equal to alpha squared divided by square root of 2 pi, integral from 0 to 1, integral from minus infinity, sorry, I forgot the square root of t here. And then I get here exponential minus x squared, x over square root of 2t minus alpha square root of t, and then square that. Right, and then dx dt over square root of t. And I've missed the extra term that I need to cancel, which is the exponential alpha square t term, dt square root of t. And then this is certainly smaller than alpha square, square root upon 2 pi, exponential alpha squared times the integral from 0 to 1 and the integral from minus infinity to plus infinity of this thing here. Dt over square root of t. Now let's make the change of variable y equal x dx over square root of t dt. And let's make the change of variable y equal x divided by square root of t. And if I make this change of variable, I'm going to get alpha square square root of 2 pi exponential alpha square integral from 0 to 1 integral from minus infinity to plus infinity. So let's do that, minus alpha square root of t, and then I get exponential minus y squared dy dt. And this is equal to alpha square divided by square root of 2 pi exponential alpha square times the integral from minus infinity to plus infinity of exponential minus y squared dy, which is certainly finite, right? Because exponential minus y squared is in L1. Okay, so that proves that the process, the dxftbt, is a H2 process, and therefore xt is the integral, the E2 integral of an H2 process, therefore it is a martingale. So this is a pretty concrete computational way of checking that something is a martingale. Okay, so in example 1, we were given a process and we were asking ourselves, is that a martingale? Now let's do something a little bit more subtle. Let's say we start with a problem and we look for a martingale that can solve this problem. And let's find how Ito's formula will help us do that. So let's go back to our favorite problem in this course, which is about the Brownian or a random walk exiting a certain interval. So as always, we define a stopping time as the infimum of time such that bt reaches a or bt reaches minus b, and we give ourselves some a and b that are some positive number. So we have shown previously that the probability that you exit through the right hand side rather than exiting through the left hand side is b divided by a plus b, and we've also seen that the expected time at which this exit happens is a times b. Now, we've shown also that the expectation of beta is 0, because bt is a martingale, tau is a stopping time, and then we use a dominated convergence argument to show that property from the fact that the expectations of the bt are constant equal to 0 for actual deterministic time. Now the question we're going to try to answer here is, what is the covariance of tau and beta, right? So some more subtle statistical information on these variables. So, okay, what is this covariance? Well, it's the expectation of tau minus its expectation times b of tau minus its expectation, right? And we can compute that because E of tau is AB and E of B of tau is 0. So what we get is expectation of tau times B of tau minus the expectation of tau, which is AB, times the expectation of B of tau, which is 0. So what we get is just the expectation of tau B of tau. Very good. So let's try to compute expectation of tau b of tau. So the idea is to use a function f t bt as our process and have it be a martingale. So the guess would be, okay, I'm just going to take f of tx equal t times x, right, in order to get this expression. But the problem is that if you do that, you would realize that, well, you don't get a martingale by taking t times b of t. Now, in order to get a martingale, you need a compensation factor. So how are we going to find out what this compensation factor should be? So let's take f of t of x being t times x, which is what we're interested in, plus some correction term, g. Okay. And, well, let's hunt for g that's a polynomial. A little bit of work will show you that this polynomial will have to be, at most of order 3. So let's take gtx to be of the form a times x cubed plus b times x squared. Now, this may not be good enough. Maybe we need a polynomial of higher degree. Maybe it needs to be genuinely a function of t and x, not just a function of x. We'll see. But computing partial derivatives of that, you will realize that you can satisfy the PDE dt ftx equal minus 1/2 of dx squared ftx. So you don't need to make your g any more complicated than this. So let's find out how that works. So let's compute dt of ftx. That's what? That's just x. And then let's compute dx of ftx. That's t plus 3ax squared plus 2ab. And let's compute dx squared of ftx, and that is just 6ax. So in order to satisfy the PDE, dt ftx equal minus 1/2 of dx squared of ftx for all t in 0, 1, and for all x in R, all we need to have is that 6a. So that was 2a. That was not 2ab here. That was 2bx. And here this is 2b. So in order to satisfy this PDE, what do we need? Well, we need 6ax plus 2b to be equal to x for all x. in R, and this is possible by choosing A equal -1/3 and B equal to 0. So if you define now ftx to be tx minus x cubed over 3 for all t and for all x, now we're going to have that ft/bt defines the martingale as soon as the expectation of the integral of dx ft/bt squared is finite. So Ito's formula will imply that. Will imply that ft/bt is a martingale, because ftx satisfies the martingale with respect to the Brownian filtration. Because ftx satisfies the PDE, Ito's formula really tells us that ft/bt is nothing but the integral, the Ito integral of dx fs/bs from 0 to t. So as long as I'm integrating an H2 process, I'm going to get a martingale. So let's check that I'm indeed integrating a H2 process. So let's compute the integral from 0 to 1 of the expectation of dx ft/bt squared dt. What is that? Dx ft/bt is here, so it's t minus x squared. So I'm computing the expectation of t minus bt squared, and then I square that dt. So let's expand that square, and I'm going to get the integral from 0 to 1 of t squared minus 2t times the expectation of bt squared plus the expectation of bt to the 4 dt, and this is equal to t squared minus 2t, expectation of bt squared is t, so 2t squared, and then the expectation of bt to the 4 is 3t squared dt. So I'm integrating from 0 to 1, what is it, 2t squared, and okay, and 2t squared is 2/3 times the derivative of t cubed, and so t cubed taken to 0 and 1 is 1. So this entire thing is 2/3, which certainly is finite. Okay, so so we have an H2 process in dx fs/bs, and that guarantees that ft/bt is a martingale. Now, if ft/bt is a martingale, we have that ft minimum tau, comma bt minimum tau is also a martingale with respect to the Brownian filtration, because we've already shown that tau is a stopping time. Very good. So what does that give me? That gives me that the expectation of ft minimum tau bt minimum tau is equal to the expectation of f00, which is 0, for all t in 0, 1. Okay, but now what can I say? Well, I can say that ft minimum tau bt minimum tau, as I sent t, okay, I've wrote that for all t in 0, 1, but this is really, I mean, all of that really is for all t non-negative. And this is important here because eventually I want to send t to infinity, and because the stopping time is finite almost surely, this goes to f tau b tau almost surely. Now f tau b tau is, you know, for every omega, say, is what? So it is given as f tau beta is tau times b of tau, tau of omega, times b tau of omega, minus b tau of omega cubed over 3. So what can I say about that? Well, beta is always smaller than the maximum of A and B. So this is smaller than tau of omega times the maximum of A and B plus the maximum of A and B cube divided by 3. And now the point is that tau is in L1. That's something we've already proven. In fact, so tau is almost surely non-negative, and its expectation is A times B. So what have we got? We've got here an element of L1, so maximum of AB times tau plus maximum of AB cubed divided by 3 is in L1, and so by dominated convergence, the expectation of f tau b tau is the limit as t goes to infinity of the expectation of f t minimum tau comma bt minimum tau, right? And that was 0 for all t anyway. So the expectation of f tau b tau has to be 0. And now what does that give us? It gives us that the expectation of tau b tau has to be equal to the expectation of b tau cubed divided by 3. But what is b tau cubed divided by 3? Well, there's two possibilities. Either b tau is a, and then I get a cubed divided by 3, or b tau is minus b, and then I get minus b cubed divided by 3. And we know what these probabilities are. The first one is b divided by a plus b times a cubed over 3. And the second one is a divided by a plus b, and that's times b cubed divided by 3. So if you put all of these things together, you can factor in an ab divided by 3 times a plus b, and this is going to be multiplied by a squared minus b squared. Okay. And you could simplify that even further, because a squared minus b squared is a plus b times a minus b. So this entire thing is ab divided by 3 times a minus b. And remember, this now gives you a very precise formula for the covariance of the variable tau and the variable beta. So it's something that, if we didn't have all of this martingale theory and Ito formula at our disposal, the idea of trying to compute that thing would be pretty daunting. But this gives us a very powerful machinery to do that without thinking particularly much. I mean, there was a bit of a guess in thinking maybe taking g a polynomial of degree at most 3 in the x variable would be enough. But more generally, we could have started with g being a polynomial of arbitrary order in x and t. You make a bit of computation and you realize, to satisfy the PD, you really don't need that many terms in the polynomial g, and you realize that the only terms that really matters are the terms in front of x cubed in the terms in front of x squared. So although I did do a bit of a guess, this is not too hard a guess. And after that, it's purely computational. You compute a partial derivative, you compute this expectation of the integral of dx of t bt squared, and then you just play out your same techniques with the stopped martingale theorem and dominated convergence, exactly as we've done to compute the expectation of tau, or the probability of b of tau equal to a in the first place. But here the martingale would have been much harder to guess in the first place if we didn't have the Ito formula to check that whatever function of t and bt we come up with does define a martingale. Okay, now that concludes the second example, and we're going to see a third one where we can now go even further, and instead of getting more refined properties about exit times of the Brownian, look at exit times of more complex stochastic processes. Again, as long as these processes come from functions of the time in the Brownian, checking that the appropriate process is a martingale is not going to be too difficult. It's going to be a matter of computing 3 partial derivatives and 1 integral. Now, for our last example, we are going to start our journey beyond using purely the Brownian as our favorite stochastic process. So we know how to handle the Brownian and function of the Brownian. We also know how to handle just deterministic function from standard calculus. Now we're going to start mixing the two a little bit. And so let's take two constants for now. Let's assume they're non-zero. And let's give ourselves two number a and b and consider a process xt that is sigma times the Brownian plus mu times the time t, right? So this has a deterministic part, we call that a drift with drift coefficient mu, and it has a random part, a genuine stochastic part, which is just a multiple of the Brownian for now. And this constant multiple, the constant in front of it, is called the volatility constant. Now we'll see that this is a very basic example of a general class of processes called standard processes, and that class is quite wide and quite powerful in terms of its modeling power. But for now, let's just look at this simple mixing of a deterministic term and a Brownian term and ask our favorite question. So define stopping time by taking the infimum of those t such that xt is a or xt is minus b, and then ask as a question, when is it that x tau is a? So this process that's not just a plain Brownian, it also has a deterministic part, decides to exit from the right rather than, well, before it exits from the left. So I'm going to look for a martingale that helped me study this problem. So let's look for a function of t and x that's going to be just a function of sigma x plus mu t for some function h. And what do I want the function h to be like? Okay, I'm going to ask it, of course, to be twice differentiable. And I'm going to fix its values at a and minus b. So I'm going to say that h of a is 1, say, and h of minus b is 0. Now, the point of that is that then I have that, what is h of 0? So h of 0 should be the expectation of h of x tau. You know, if the entire reasoning works. So if h of x tau is a martingale, then its expectation should be constant. You should be able to go to the stopping time, and then this would be the probability that x tau is a times h of a plus the probability that x tau is minus b times h of minus b. So by making the choice h of a equal 1 and h of minus b equals 0, I would get that this is exactly equal to the probability that x tau is a. Right, so, okay, so we need to show, so when I say we should have, so we have that if two things happen, so if xt is a martingale, sorry, not ht, h of xt is a martingale, that's the first thing I need to prove, and the second thing I need to prove is that h of xt minimum tau tends to h of x of tau in L1. So let's put it this way. The expectation of h of xt minimum tau minus x of tau, h of x of tau tends to 0 as t goes to infinity. So I'll get that from a dominated convergence argument. Okay, so the point is to find an h, right, such that f of t of x defined by like that gives me a martingale. So what do I need? So to prove 1, we first need that dt of ftx is minus 1/2 of dx squared of ftx. Okay, so let's compute that. What is dt of ftx? It is mu times h prime of sigma x plus mu t. That's just by the standard chain rule. And what is dx of ftx? It is sigma times h prime of sigma x plus mu t. And what is dx squared? It is sigma squared times h second of sigma x plus mu t. Okay, so I want to satisfy the PD dt ftx equal minus 1/2 of dx squared of ftx for all t and for all x. Now this certainly will happen if I have that h prime of y is equal to minus sigma square over 2 mu times d times h second of y for all y in R. Now that's an ordinary differential equation, and certainly any function that satisfies h prime of y equal some constant times exponential minus 2 mu over sigma prime of y, even plus another constant c prime for all y in R. Actually, forget that. Any function of that form will certainly satisfy the ordinary differential equation, because if I take the second derivative of well, the first derivative of h prime, so the second derivative of h, it would satisfy the equation here by differentiating that. So anything of that form would do, which means that if I were to take an h of this form, exponential minus 2 mu sigma squared y plus some c prime, for some c in R, for all y in R, for some c and c prime in R, then this would give me a solution. So I just need to pick an h of that form, and I have two parameters c and c primes that I can freely choose, and I will choose them such that I have h of a equal to 1 and h of minus b equal to 0, right? Because that's another property of h that I need to have. So anything of this form will make f of tx satisfy the PDE, but then on top of that I want these two conditions, and I'm going to fix my c and my c prime such that I satisfy these two conditions. So okay, well, that's a bit of computation. I want 1 to be equal to c exponential minus 2 mu over sigma prime a plus c prime, and I want 0 to be equal to c exponential minus 2 mu over sigma prime times minus b plus c prime. And so this means that I want what? I want 1 equal to c times exponential minus 2 mu over sigma squared a minus exponential 2 mu over sigma squared b. Okay, so that gives me my c, and then I want c prime equal to minus c times exponential 2 mu sigma square over b, which will give me my c prime once I have my c. So plug all of these together, and I have that if h of y is equal to c, so 1 upon exponential of minus 2 mu divided by sigma squared a minus exponential 2 mu sigma squared b, that's time exponential minus 2 mu over sigma squared y, and then plus plus c prime, and c prime is minus c, that was the constant c, so minus exponential 2 mu sigma square b for all y in R. So if I choose my h of y exactly in this form, then h of sigma t plus, h of sigma bt plus mu t, this process here is such that, I should say, is such that dt ftx is equal to minus 1/2 dx squared of ftx for all t and for all x, where f of t x is h sigma x plus mu t for all t and for all x, and h of a is 1, h of minus b is 0. So what we still need to show, for instance, it remains to show, we then show that we're integrating an h2 process, so that the expectation of the integral from 0 to 1 of dx of ft bt squared dt is finite. Right, so let's do this computation of an integral. We've computed our partial derivatives. We have a process that has the potential to, so h sigma bt plus mu t could be a martingale. It will be a martingale if, when I take the first derivative in x, I end up with an h2 process. So let's compute that and see what happens. So expectation, integral of 0 to 1, dx ft bt squared dt, what is that? This is, so, okay, what was dx ftx again? It's here, it was sigma times h prime. So I'm going to pick up a sigma square, and then what was h prime? There's a number in front, this 1 upon c, which I really don't care about. So it's sigma squared divided by exponential minus 2 mu over sigma squared a minus exponential 2 mu over sigma squared b, and then this is time expectation of exponential minus 2 mu over sigma squared of bt. Is that right? What was my h prime? My h prime, okay, I differentiate that and I plug in not bt but sigma bt plus mu t, okay, and then this is squared, so you pick up a 4, and then because you've differentiated, you pick up a 4 mu squared over sigma squared, which, okay, the sigma squared here cancel, and you get a 4 mu squared in here. Okay, now I really don't care about that number at the front, because all I'm trying to show is that this is finite. So this is finite if and only if the integral from 0 to 1 of the expectation of the exponential of minus 4 mu over sigma squared times sigma bt plus mu of t dt is finite. So let's do this computation. And again, I know the density of bt, so what I get is the integral from minus infinity to plus infinity of 1 upon square root of 2 pi t exponential minus 4 mu upon sigma squared times sigma x plus mu t, and then all of that is multiplied by exponential minus x squared over 2t, and then that's dx, and then that's dt. So we're going to make a change a variable here. Well, first of all, let's complete the squares. So I want to show that this is finite, and this is equivalent to this exponential minus x divided by square root of 2t. What is it? I want the cross term to be 4 mu over sigma squared. So okay, so this is plus 4 2 mu over sigma times square root of 2t. Okay, and then you square that. Okay, and then you pick up, you still have an exponential minus 4 mu squared over sigma squared t, and an exponential 4 mu squared over sigma squared times 2t. So that's 8t. And all of that is dx dt. And I want that to be finite. Now, okay, so let's compute that. Again, I have 0, 1, integral from minus infinity to plus infinity of 1 upon, so let's make a change variable straight away. So let's make the change variable y equal to this entire thing, and then I get that this is equivalent to exponential minus y squared exponential, what is it, plus 4 mu squared over sigma squared of t dy dt being finite. And now this thing is equivalent, this is true. This is certainly finite because well, because this here is a finite number and this is in L1 of R. Oh, let's write it like that. Okay. So we have a integral. Okay, therefore h of sigma bt plus mu t is the integral from 0 to t of dx of f of s bs dbs, and that's for all t, and dx f s bs. This process is in h2. I only did it for h2 of 0, 1, but it's really h2 of 0t for any time interval t. Now, what that time interval 0 to capital T. So what that gives me is that h of sigma bt plus mu t is a martingale. Yeah, there's an interesting point here. I mean, being a martingale is a property for fixed t. So I don't need to be able to integrate in here all the way to infinity. I only need to be able to integrate on any finite time interval. And I only did it up to 1, but it's exactly the same argument that will give it up to any fixed number capital T. And that's good enough to guarantee that I have the martingale property. Right? You could do it up to any finite time capital T. Now, okay, so I have a martingale here. Now, what that tells me, because martingale have constant expectation, that h, and that was my process xt, remember? So this tells me that h of xt minimum tau is also a martingale with respect to the Brownian filtration again. And constant expectation tells me that the expectation of xt minimum tau is the same thing as h of 0 for all t positive. Right, now in the meantime, xt minimum tau is certainly always smaller than what? Okay, we have to remember what that thing is. This is x, this is 1 upon some number, so 1 upon exponential minus 2 mu over sigma squared a minus exponential 2 mu over sigma squared b, whatever, just a number, times exponential minus 2 mu over sigma squared of x of t minimum tau, and x of t minimum tau, what's the worst that it can be? The worst that it can be would be, okay, I gotta be careful because this is, okay, so this is smaller than this, plus the absolute value of, well, an exponential is positive. This number at the bottom here would be negative, and the worst that this can be is at minus b, right? That's what makes the exponential the largest, and then I have that twice. Now that doesn't really matter what this number is. The point is that xt minimum tau is always smaller than a fixed number. That is to say, it's smaller than an element in L infinity. That is to say, it's smaller than an element in L1. So by dominated convergence, and that was not x of t minimum tau, but h of x minimum tau. So by dominated convergence, I get that the expectation of h of x tau is h of 0. And remember, we seen at the very beginning that, of course, this expectation is nothing but the probability that x of tau is a, because h of a is 1 and h of minus b is 0. And now what is h of 0? Well, we have an explicit formula for h, and h of 0 is exponential minus 2 mu over sigma squared times 0 minus exponential 2 mu over sigma squared times b divided by exponential minus 2 mu over sigma squared a minus exponential 2 mu over sigma squared b. And so there you have it. The probability that x of tau is a is, what is it? It's exponential 2 mu over sigma squared b minus 1 divided by exponential 2 mu over sigma squared b minus exponential minus 2 mu over sigma squared a. Okay, so this is a fairly complicated expression, but this is very explicit, and that tells you exactly how this process, that is a mix of a Brownian, a multiple of the Brownian, sigma bt, and a deterministic process will exit the interval through the right rather than through the left. Now, it's nice to run some reality check in this formula, right? And one of the reality check is what happened to this formula. So let's call this quantity, so this is a function, let's call it, I've got an f, I've got a g, I've got an h, let's call it k of mu sigma squared, mu and sigma. So what happened to k mu sigma as mu tends to 0? So if mu tends to 0, you're going to pick up a derivative at the top, and this derivative is going to be 2b divided by sigma squared, and then that's divided by, I'm sending mu to 0, so I get a 2b divided by sigma squared plus 2a divided by sigma squared. And okay, so you simplify that, this is b divided by a plus b, which makes sense, right? Because if mu were to be 0, you would be just dealing with a multiple of the Brownian, and you would see that you get that same exit time as before. Okay, now in the same way we could send sigma to 0, and then what do we get? We get that k mu sigma tends to, that depends a bit on mu. If mu is positive, then this term, as sigma goes to 0, goes to infinity, this term goes to infinity, and this term goes to 0. And so what you get is 1, right? Because this term is exactly equal to that term, as sigma goes to 0 if mu is positive. And on the other hand, if mu is negative and you send sigma to 0, this goes to 0, so the whole top goes to -1, this goes to 0, but on the other hand, this goes to infinity. So this entire thing will go to 0 if mu is negative. And that makes perfect sense, because if mu is positive, it means you have something that, you know, deterministically moves to the right. If mu is negative, you have something that deterministically moves to the left. So the probability of exiting to the right before exiting to the left is 1 if you're just moving to the right, and it's 0 if you're just moving to the left. So all of that is captured by our formula by taking limits as mu or sigma approach 0. Right, now that finishes that example. There's many, many more we could treat like that, just applying it to a formula, computing two partial derivatives, computing a integral using the density of a Gaussian, and deriving that a certain process is a Martingale from there. We're going to leave those examples here, and we're going to see a more general instance of the idea that we've been using in that last example. So the idea that we've been using in that last example was really some application of the chain rule. So define our ft bt as a function of another process x of t. So we're going to now put that into a more general framework, such that in the same way as we have Ito formula as the analog of the standard of the fundamental theorem of calculus, if you want, we're going to have a stochastic analog of the chain rule.